Okay. So may I start with my sincere thanks to you, Professor Kia, for organizing this Resilience Catalyst talk. And I am Petra Malezan from the UNESCO Chair on Intersectoral Safety on Disaster Risk Reduction and Resilience at the University of Udine in Italy. And with our chairholder, Professor Grimatz, who is also participating to this meeting, we really warmly welcome you to this fourth webinar of the Resilience Catalyst series. What is this series? This initiatives, the Resilience Catalyst initiatives, is born under the umbrella of UNESCO and is part of the Resilience Program, that is a program supported by the Central European Initiative and developed by our UNESCO Chair. The goal of the Resilience Catalyst series is to begin exploring the role of UNESCO chairs that are focused on disaster risk reduction and resilience, with the goal to consider the complex interplay occurring between the main UNESCO pillars, education, science, culture, with the goal of transforming governance for building resilience to disasters. So after our initial meeting we had last year, we launched this talk series to showcase the work of the different UNESCO chairs participating to these initiatives. So far we had three insightful sessions from the UNESCO Chair on Disaster Risk Reduction and Resilience Engineering at the University College of London of Professor Dayala. From the UNESCO Chair on Water, Energy and Disaster Management for Sustainable Development at the Kyoto University, led by Professor Tachikawa, and from the UNESCO Chair on Water-Related Disaster Risk Reduction at the University of Ljubljana, led by Professor Mikos. So these three chairs develop topics different, but they are interconnected by the focus of resilience to disasters. Also this your talk is very appreciated within this series, since your UNESCO Chair in Informatics and Multi-Hazard Risk Reduction at the Loughborough University is really focusing on the main topic of our series. So Professor Kiwa Liang, we really thank you for organizing this talk, and we extend our sincere gratitude to Dr. Cheng, Dr. Jiang, Dr. Qing, sorry for mispronunciation, and we thank you for organizing this session on high-performance multi-hazard modeling for disaster risk reduction. And you can find the record of all this session in the Resilience Catalyst webpage, and we will share the link in the chat in a few moments. So without further delay, Professor Kiwa Liang, the floor is yours. Thank you so much.
Yeah, thank you very much, Peter, for the introduction about the Resilience Catalyst talk series. Yeah, I'm really honored, I think, to be invited to introduce our UNESCO Chair and also the research activity, I think, in the following 1 hour. Yeah, my name is Kiwa Liang. So as introduced by Peter, I think I'm from Loughborough University in the UK. So a couple of years ago, I think our UNESCO Chair, IMRR UNESCO Chair, was approved by UNESCO and then to set up in Loughborough University. Meanwhile, together with the International Center for Informatics and Disaster Resilience, ICIDA, on the top right, the logo is there. So our chair, obviously, what I will introduce, briefly later on, we focus on the informatics, basically emerging technology, and then to support disaster reduction. So today, together with me, I have Dr. Huili Chen, and then Dr. Jinghua Jiang and Haoyang Qin, and then deliver this seminar together with me. And then they will give themselves a brief introduction when they start to talk. So I'll start again talking about the overall, subject and also our activity, and then transit to them to talk about specific, aspects of the research in our chair. Can you help me to move the next page, please, Hao-Yang? Yeah, so obviously, because of the chair, in this series, all related to disaster risk reduction, I'm sure this figure, everybody already know that, seen that. So I think this shows the numbers related to disaster in the last 2 decades. So no matter considering the number of disasters, created by natural hazard, and also the number of people affected, and then economic losses, they all, all of them, multiplied, in the last, I think decade compared with a decade, I think before that. So for that reason, I think disaster risk reduction, DRR, although it's not written in any specific, I think SDG, but they're center, to the SDGs. And then center to these sustainable development goals, or sustainable development agenda of the UN, and also emphasize, I think by different government, as the, their top priority, in terms of sustaining, social economic development, and also achieving the net zero, for example, in the UK government. So, but we know that I think all of the disasters, they not really happen, I think in a silo way. For example, flooding, I think they may be introduced by rainfall, but rainfall can also trigger landslide and then debris flow, and then other I think hazardous process. And also all of these hazardous process can interconnect with the social sectors and then create I think cascading systematic risk. So I think, however, our current practice in terms of disaster risk reduction is still mainly siloed. That means we don't really have a well-developed approach, or practice to manage this kind of systemic risk. So I think that's, I think the kind of problem we're addressing, I think hopefully through this chair, and also our sister chairs across the world. And then the problem is complex because again involving complicated cascading hazards and then interacting with social systems. So that create again complex, interconnected, and systemic risk. So there's no easy solution. There's no I think well-fitted science at this moment to address this. But however, we are kind of in a very good time, and then because of the rapid technology development in recent years, that provide actually unprecedented opportunity for us to really develop approach and then to deal with this. So for that reason, I think I put I think a very simple paragraph in here. You show that the great challenge we're facing, I think natural hazard, and also that's worsened by climate change and also population growth, urbanizations, and a series of drivers making things more and more complicated, as I mentioned before. But meanwhile, all of this kind of technology development and then provide, I think, opportunities. Now we are facing, I think, more data, than ever. And then the world is more connected than ever. And also we have a much, I think the ever more powerful, I think, computational tools in here, like AI and then hypercomputing, things like that, so that we can really tackle, this challenging field. So in here, again, the task, for us, I think, not only our group is across the world, is how we can bring this technology together and then to develop new approach and then help us unlock this kind of, I think, scientific challenge and then practical challenge and then do a better work. So, so that's the main purpose, for us to set up the UNESCO Chair mentioned. So I think the IMRR UNESCO Chair here in Loughborough. So I think the chair covering, I think a wide range of, I think objectives covering, research and also foster collaboration across the world and also support, capacity development, especially in low and middle income countries like Africa and Southeast Asia, those, I think different countries where the access to data and technology is lower. And then how we can really develop fit for purpose technology to help, I think to learn from each other and also to help, do a better job in terms of helping with disaster risk reduction. This is a core, objective, of this chair as well, and also education training, so that that's a part of the capacity development. And then this is, I think the chair is established again by me and also, not only myself and also a group of leading academics here in Loughborough, and then coming from different subject area. So I don't have time to introduce them one by one, but you can see the photos, in this little, I think corner in here. You can find out more information on our website. And then again, to deliver the key objective of the chair, and then we have a range of activities, I think which I will introduce about research later on. But then the key activity we're engaging now is to set up the global partnership to support resources, knowledge sharing, and then to support, again, to foster international collaboration and a multidisciplinary collaboration, and also global capacity development for disaster risk reduction. And then the initiative we set up, which is launched by the chair and also together with a leading university in China, Chengdu University of Technology, who is a world leader in the geohazard risk assessment and research. And it's called SIMA, the Global Partnership for Smart Informatics and Multi-Hazard Reduction. So again, you can see we have 4 key objectives in here. And then first, create a transdisciplinary forum, for us to collaborate. And secondly, and it's advanced scientific innovation in terms of bringing, all of this leading, or emerging technology into the field of disaster risk reduction. And then, although it sounds technical, I think more technical, focus, but the partnership is entirely multidisciplinary. Because in nowadays, we don't think, I think a silo way to handle the disaster risk reduction is a feasible way. So I think it's really like covering all subject area related to this goal. And then promoting open knowledge and capacity building, and also bridge science and policy. So I think, again, we don't really have time to give detail, and then you can look into our website and then to find out more details. And then since the setup, and then we have our first, international conference, SIMA 2024, happened here in Loughborough last September. We welcome about 200 leading academics and researchers from across the world, coming to Loughborough and then to have this launch conference. Now we schedule our second, international conference, SIMA 2025, in the hometown of Panda, Chengdu in China, I think in 2025. And then we're going to issue our third call of object, very soon. So then hopefully, I think we can see you all, in Chengdu, I think later in September. And then also we launch our webinar series. So I think to bring together the world-leading, really world-leading experts, to share their latest research and also share the insights in this field. So I think this is the 4 webinar series we already, 3 of them already happened, and then the other one is happening next month. So I think each of this webinar, attracting about 200 to 300 people, attend each of them. So I think please also, again, sign up and also I think follow and then to find out a bit more. Okay, so this is the activity coming to the research. I think again the chair's focus on developing and applying emerging informatic technology, to support disaster risk reduction. So one core research area we focus on is developing high-performance modeling technologies to support multi-hazard, simulation and also forecasting, risk assessment and management. So the flagship model we are developing and maintaining is called HiPIMS, High Performance Integrated Hydrodynamic Modeling Systems. So basically, it's a hydrodynamic model we developed, for forecasting and modeling across, for example, a whole city, a whole catchment of thousands of square kilometers, but in meter level resolution. So to provide high detail, high resolution detail, to support assessment and risk management. And then, but like I mentioned before, for example, flooding or rainfall can not only, I think, introduce, flooding, but also I think other process like landslide and things like that. So, so we also, I think, developed a model for other processes as well, which I will mention later on. And then this is the HiPIMS application in a large catchment in the UK. So in the northwest of England, 2,500 square kilometers Eden catchment. So you can see that, we applied the model to reproduce an event in 2020, happened in 2025 at 5-meter resolution, across the whole, catchment. I think similar to detail, flooding process from rainfall, I think runoff, overland flow, inundation, and then, I think to really assess the impact, on a city like, the one showing in the figure. So looking into performance, you can see that, simulation involved, again, 2,500 square kilometer of catchment, and 100 million cells, and then 5-meter resolution. But we only need, I think about 40 hours to finish, I think 96 hours, simulation. So really beating the real time. Again, in terms of multi-hazard, I think modeling, we really need a tool, to simulate this kind of cascading, I think has the process. So I think on the top left, you can see, the high PIMs for simulating landslide. And then the top right corner is the hazard chain created by rainfall. Basically, a landslide in upstream, and then coupled with the flash flooding, and then develop into debris flow, and then impact a village downstream. And then sediment transport, water quality, I think on the bottom left. And then also, I think during flooding. And then we can see cars and muscle beans, lots of floating debris carried along by flooding. And then so we also develop a model to simulate this kind of complicated, process, interacting with flood wave and also infrastructure like bridges, I think something like that, so that, we can, again, we present better the real world in terms of, I think developing better informed, strategies for risk assessment and management. So sorry to overrun a little bit, so now I hand it over to Hao Yang and the team to talk about, I think more specifically, I think different aspects of the research. So Hui Li, now I hand it over to you. Thank you.
Okay, thank you, Qiuhua. Can you hear me? Yeah, okay, yeah. A quick introduction about myself. I'm Hui Li Chen. Yeah, currently a senior lecturer in water engineering in Laval University, and also a member from Qiuhua's research group. Today I will introduce some of our work about GLOF's glacier lake outburst flooding in Nepal, and also is also part of research output from the project WEACT, web-based natural dam burst flood hazard assessment and forecasting system. Actually, this project was funded by the UK's Natural Environment Research Council, and it is led by Qiuhua. So before I go into the research side, I will give a quick introduction about our project. In this project, we focus on GLOF's glacier lake outburst floods. We know GLOF's is one of the most serious natural hazards in populating mountain regions across the globe. And also because of deglaciation due to climate change and also ongoing changes in land use and population distribution, currently the risk of GLOF's has been substantially increasing. And also our case study, our area of interest focus on Nepal. In Nepal, GLOF's threatened thousands of people, hundreds of villages, and basic infrastructure downstream. And also, GLOF early warning system is a very effective means to mitigate the risk, but it is heavily rely on instilled measurement. However, rugged terrain with harsh weather conditions made it quite difficult to access instilled measurement. And currently, effective early warning and risk mitigation strategies are still lacking in Nepal. So through our project, we successfully developed new techniques for multiple hazard risk assessment. And also we developed the integrated Earth observation-based risk monitoring with a web-based hazard forecasting and warning system. We also transferred natural hazard monitoring and modeling approaches developed in this project to other countries and also in other areas in South Asia. Next slide, yeah. Okay, based on the developed model and also the developed evaluation framework for GLOF risk. So we try to evaluate GLOF risk at the national and regional scale. But when we are trying to do this, we still face some challenges. The first challenge is the data issue. everyone knows that high altitude conditions has constrained our ability to acquire detailed spatial data for multiple lakes across a large scale. And another challenging for us is the model issue. Although currently a range of physical-based hydrodynamic model has been developed and applied, but actually they required a huge amount of computation and faced substantial demands for computation resources when applied at a large scale. So in order to tackle these two challenges, we developed a new framework for the evaluation of global risk at the regional or national scale. Next slide. Next one. Okay. Actually, in our framework, there are 4 main parts. The first part is that with the availability of multiple temporal imagery, or random forest model based on a set of predictor variable. So it's used to map the location and also extent of water surface for glacier lake under different hydrological conditions so that we can produce the maximum extent of lake water surface. Next part. And by using the maximum extent of glacier lake water surface, we will employ the established basin model so that we can predict the glacier lake conditions and also the dam breaching process. The basin model will allow us to estimate the full range of global outflow discharge through the breach. Next one, please. And then different global scenarios feature a wide range of outflow discharge hydrograph are then sampled into to drive the GPU-based hydrodynamic model for the simulation of dynamic flood dynamic resulting from GLOFs. Next one. And at the same time, we collect data from different sources, including OpenStreetMap, satellite imagery, Google Earth, local archives, so that we can develop the exposure dataset detailing like buildings, roads, agriculture, hydropower plants, and so on. And then we combined the exposure dataset and also the flooding simulation result from the 2D hydrodynamic model, including like the inundation frequency, distribution of water depth, flow velocity, and flow arrival time. We can easily identify the exposure, and also by using the water depth damage curves, we can evaluate the damage extent. Okay, this is the overall framework. And for our case study, here we still focus on Nepal. And for the study lakes, we focus on the 21 lakes that have been identified as potentially dangerous glacier lake. Next one. Okay, I will go directly into our evaluation results. Okay, this is result from for the glacier lake water surface extraction from Sentinel-2 imagery. The left figure shows some results for some representative glacier lake in Nepal. Actually, from this figure, we can see some lakes like the Luding Lake, Chorpa Lake. So these lakes are covered by open water throughout the year. But for other lakes, some unnamed lakes, they are not consistent covered by open water throughout the years. And by directly using the interpolation results from remote sensing, so we can easily calculate the area under different water occurrence frequency for each lake. And here we will directly use the maximum extent of lake area to represent the most serious scenarios to evaluate the global risk. Next one. Okay, I have introduced that we will directly use the established basin model to predict lake values and also peak discharge. So here in our case study, so we get 100 estimate of total value for each lake, and we also get 1 million estimate of potential flood values and peak discharge across the lake under the most extreme scenario, that is all the lake water will be released to cause growth. And next one. Yeah, from our modeling result, we found that the lower Barren Lake shows the highest median flood value and peak discharge. And next one. Oh, yeah. In order to validate our modeling result, here we also do some comparisons between the calculated value with the invested values. From the table, we can see the calculated values generally aligned with the invested values. Yeah, next one. Okay, then 100 scenarios are randomly selected from the total of 1 million peak discharge scenarios per lake. And then the bridge hydrograph serves as the boundary conditions for our HyperIMS model. So the HyperIMS model operates on a multiple GPU and multiple node high performance programming framework to simulate growths. And the resulting flood dynamic will provide the essential data for the subsequent evaluation of the potential growth, exposure, and damages. Next one. Okay, then we can estimate the direct damage to buildings and also other exposed objects, for example, roads, agriculture, and so on, so that this can be achieved by using appropriate depth damage curves. And we can evaluate how serious the damage will be. From our evaluation, we can see the Chorupa Lake, Lower Barren Lake, and Salak Lake. They will cause the most serious impact of growth on buildings and roads. And also something that we need to note is that there are 4 unnamed lakes that have the potential to impact more than 100 buildings. Next one. Yeah, apart from the exposure and impact damage, we also identified which hydropower plant can be potentially impacted by growths due to these 21 lakes. And from our evaluation, we found that 12 existing hydropower plants and 38 hydropower projects that have been granted generation or survey license can be potentially impacted by these growths. Okay, this is our modeling, this is our evaluation results. Actually, from our result, we can see this result can provide a more clear big picture for the overall impact and also impact for each lake, and also for the whole Nepal country. And also at the same time, the exact location for each exposed buildings, each exposed infrastructure, agriculture area, and roads. These types of information can provide very valuable information for targeted risk mitigation, risk management, and so on. So this is why we carry out this work. Okay, this is what I want to share for today's lecture. Yeah, now I hand over to Jinhua.
Hello everyone, my name is Jinhua Jiang, and I'm currently the research fellow in the Loughborough University. So my research focuses on using the numerical method to evaluate the nature-based solution performance against the flood risk. So today I will share a case study which is conducted in Canton. We try to evaluate the feasibility and the performance of the nature-based solutions in Canton against the pluvial flooding. So the reason we focus on the pluvial flooding is we can see that there are a lot of factors that can cause the flooding in the Canton. However, one of the research which is conducted in the 2009 show that the 20% of the flooding are caused by the rainfall. So in this case study, we first focus on the pluvial flooding and then to see how the nature-based solution can against the pluvial flooding risk. So one of the reasons for the flooding in this city is because of the low topography. It can be ranged from the 0.6 to the 1.2 meter above the sea level. The second reason is the poor drainage capability. According to the Canton University, and the city will still be flooded after the rain ended about 2 to 3 hours. Another reason is the climate change. The rainfall in Canton areas is characterized with the concentrated extreme events. So the rainfall intensities ranging will from the 50 to 100 millimeter per day, usually last from the 30 minutes to 2 hours. So therefore, it's very important to mitigate flood risk by relieving the silver drainage system burden, especially during the extremely heavy rainfall events. So nature-based solution as actions to mimic the natural pre-development drainage of the site has been widely proposed as the measures to reduce the flood risks due to the less demanding cost, especially compared to the traditional gray infrastructures, especially in the low middle income countries. So there are a lot of measures such as the rain garden and the infiltration trench, swales, and the previous pavement. So commonly, the method we use. So in this case study, we try to evaluate these kind of nature-based solutions, the feasibility and the performance of them in the canton. So commonly, the numerical modeling methods are applied to help us to design and evaluate the performance of the NBS. So the conventional nature-based solution modeling is based on the hydrological models or one-way coupled nature-based solution model, which use the nature-based solution modeling results to drive the following hydrodynamic modeling. So such kind of models are not capable of describing the physical interactions between the overland flow and the nature-based solution measures. So here in this study, we integrated a hydrodynamic model for the nature-based solution modeling is proposed. And we try to overcome these kind of limitations, and we can provide a better simulation of the flow process interacting with the source, with the nature-based solution measures with this framework. So basically, this framework contains two components. The first one is a surface flow modeling, which is conducted by the HIPIMS, and the second one is the nature-based solution modeling, which I modified the low-impact development modules in the swing and couple them into the HIPIMS. So we use this framework to evaluate the performance of nature-based solution. So for the case study, can you help me to next? Yeah. So first of all, for the case study, we do a model calibration. The calibrated parameters are used in the following simulation. We conducted a 5-year, 10-year, 20-year, 50-year, and 100-year return period rainfall intensities, and all within this catchment. And these results will be considered as the baseline results to compare with the nature-based solution scenarios. So we can see that the flooding spreads following the increasing of the rainfall intensity, and especially especially in the urban areas. So in the following settings, we try to conduct different nature-based solutions applied with different rainfall scenarios to evaluate the performance of these kind of measures in the urban areas. Especially, we focus on the key infrastructures, which include the schools and the hospitals. So the first nature-based scenarios are the green roofs. So we can see that we will apply the green roofs around the school areas and the hospital areas. So we can find that the green roofs can significantly reduce the flood inundation during the moderate rainfall events. However, the effectiveness of decrease during the extreme events due to the runoff from the non-roof surfaces, which means that maybe we should choose some alternative method or alternative nature-based solutions around these two areas. So first of all, let's look at the school areas. In the school areas, I choose the bioretention cells, try to deal with the 20-year rainfall intensity. However, we can see that there are still some flooded areas around these school areas. So I try to look into the hydrology performance of the bioretention cells. Next page, please. This doesn't work. Yeah. So the soil layer reaches saturated status with the 20-year rainfall. However, when we look at these areas, we can find that some cells stay at unsaturated conditions at the end of the simulation, which means however, when we look at the roads around these areas, we can see that there are still some flooded inundation depths around this road. So which means the treatment capacity is not fully used. So it suggests that the only rainfall is collected in these cells, and there is no more runoff flows into the cell. So this cell, when we analyze the DEM conditions, we find that these cells are located upstream. So it results in a limited capacity in runoff collections. Therefore, regarding the inundation areas, this design of the upstream bioretention cells is not reasonable. So this is how we evaluate the feasibility of the bioretention cells around the school area. Around the hospital areas, another alternative method we choose is the rain garden. And according to the green roofs and the green roof scenarios, we find that the green roofs cannot deal with the 50-year return period of the events in these areas. So this is the inundation depth with the 50-year rainfall intensity. We can see that here is the hospital, and there is no obvious inundation around these areas. However, we found that there is a sudden velocity increase in these areas. So we calculated the hazard rating, which is related to the velocity in this area. We found that although there is no obvious inundation on this road, the hazard category is still within the moderate hazard, which means more considerations should be included that if more uncertainty risks are involved due to the increasing velocity, which is caused by the application of the SARS. So here is the modeling performance. The total catchment is 5.3 square kilometers. And I used the 45 minutes simulation time against the 3-hour event. So basically, according to this case study, we can say that not only the runoff or the maximum depth can be used as the assessment matrix. Some other metrics like the velocities and the hazard rates and the performance of the performance of NBS can also be included with this developed modeling framework. And however, currently the spatial distribution of this kind of nature-based solution are decided by myself. So we try to understand. We try to find out a way that the find a tool which can help us semi-automatically place the nature-based solutions in the space. So here we try to develop a GIS2-based nature-based solution distribution framework. So first of all, we're doing catchment analysis, and in terms of the flood risk score, DM score, and the slope score, all these analysis will classify the nature-based solution suitability, and then combine with the land use map, and to try to find the most suitable nature-based solutions in the most suitable places. Here is one of the example. So here, this map is the areas susceptible to the flooding in Canton. And here is an example of the semi-automated framework to identify the most suitable locations for nature-based solutions. The blue one is the green roofs, and this one is the rain gardens, and these areas are the infiltration bioretention cells. So I also applied the simulation with this different scenarios. We can see with the current rainfall event and the future rainfall event, we can analyze the decrease rate of the inundation area with these different scenarios. However, currently this is the preliminary research, and we can also consider in couple with the human activities, which can provide more information for our framework to help us design and evaluate the nature-based solutions. So that's the presentation from my side. Hao-Yang, I think you can take over.
You are muted.
Did I mute? Oh, okay. Thanks, Jinghua, and good afternoon, everyone. My name is Hao-Yang. I'm currently doing the postdoc in Loughborough University. I'm pleased to introduce our research on the high-performance coupled human and natural system, which is called Transmodeling Framework for Flood Risk Assessment and Emergency Management. As my colleagues have already mentioned, urban flooding poses a significant risk to the communities over the world. Traditional flood risk management strategies often focuses on the physical aspects of flooding, such as predicting water levels and designing infrastructure. However, it is equally important to consider the human activities and the behaviors during the flood event, which may involve with the flood dynamics and even alter the flooding processes. This is where the transmodeling framework comes into play. The framework is designed to integrate the human and the natural systems to provide a more comprehensive approach to the flood risk management. This figure shows the structure of the trans framework we proposed for the flood risk management. On the left, we have the physical subsystem, which simulates the flood hazard based on the input data such as rainfall, topography, and infrastructure conditions. This subsystem determines which areas are exposed to flooding. And on the right, we have the human subsystem, which models how, for example, how the individuals, households, and organizations respond to the flooding situation. These two subsystems are dynamically linked, meaning that the human actions like deploying setbacks or flood defenses can alter the flood progression. While the changes in the flood conditions will also influence the human behaviors in return. And for the flood simulation in the physical subsystem, we use high beams. Since my colleagues have already covered its details, so I'll move on to the human subsystem. For the human subsystem, in the transmodeling framework, we use the agent-based modeling approach. This approach supports the simulation of the integrates between agents and the environment. The agents can represent a wide range of entities, including individuals, households, communities, and governments. We state the individual and organizational agents with specific features and behavior rules to explore their activities during the flood event. We use the toolkit Flame GPU or Reposeful Python to support the parallel simulation based on the high-performance GPU and CPU architecture. And this guarantees the model efficiency at a large-scale real-time simulation. We have applied this trans framework in several real-world flood events. In the first case study, we simulated a flood event in Eden Catchment, UK, at a 10-meter resolution, where we modeled the responses of 70,000 households. these households behave according to the different conditions and status, and we explored their activities with receiving flood warning, noticing the changes in flooding and communications between households. The simulation results show the accurate predictions of flooded households and financial damages. We compared the scenarios with and without the early warnings and household response to assess the effectiveness of the flood management and highlights the importance of considering the real-time human responses in the chance modeling. And we also analyzed the distribution of the effective and ineffective sandbagging areas to inform the sandbagging strategies. For example, for the areas with effective sandbagging, the government could prioritize the sandbag provision, set up community sandbag stations, and encourage sandbag self-preparation of the communities to improve their flood resilience. And for the areas with ineffective sandbagging, alternative emergency measures like applying the temporary flood defenses and mobile pumping could be considered. And our second case study focused on the dismal flooding event in the urban area of Clyde City, UK, at a 1 meter resolution. Here we explored the effectiveness of the temporary flood defenses with timely warning and governmental real-time decision-making. The results show how timely the interventions could significantly reduce the flood inundation and the financial damage. As we can see from the figures, with the installing the flood defenses in advance, a large area could be protected, and even only relying on the real-time decision-making, the temporary flood defenses still played an important role in the mitigating flood impacts. And we also explored how limited resources could affect the efficiency of defense strategies, helping the authorities to prioritize their deployment efforts. In our third study, we focused on the pluvial flooding in Canton City, Vietnam, where we integrated the reinforcement learning, an AI-based approach into the decision-making process for the mobile pump deployment and scheduling. We put the human-related factors into the decision-making processes and set the reinforcement learning agents with water depth, population density, and the number of the flooded buildings as the observation metrics. And we use the risk reduction extent as a reward. And to manage the complexity of the urban environment, we structured the domain into 15 higher level zones, each of which was subdivided into 16 smaller zones for more localized decision making. We compared the reinforcement learning guided strategy with the traditional pump deployment strategy that focuses on the lowest lying locations, which are more prone to water accumulation. And we evaluated the strategies during the concurrent pluvial flooding and the post-rainfall pluvial flooding events. And the results show that the reinforcement learning guided strategies provide significant improvements in the flood risk reduction for both event types. So for the take-home messages for chance modeling, this framework provides a high-resolution simulation for the two-way coupled human and natural systems interactions across a large domain. And it provides a new tool to assess the real-time flood risk by taking into account the dynamic exposure and vulnerability. And third, it offers a more accurate way to assess the flood risk and explore the role of different mitigation measures like the early warning, sandbagging, and temporary flood defenses, and mobile pumps. And furthermore, the application of the reinforcement learning opens new opportunities for the AI-driven flood risk management strategies and decision-making. That wraps up our presentation for today. Due to the time limitation, we could only provide a brief overview of our research's focus and activities. If you'd like to learn more about our work and the academic activities of the UNESCO Chair in IMRR, we encourage you to follow us. We are more than happy to discuss further and answer any questions you may have. Thanks for your time and attention.
Thank you. So I think, Peter, we have 10 minutes, because we more or less, can welcome any question. If there's any question or discussion, I think, please, feel free. I don't know how that works, either, on the Q&A text box, or, or directly raise your hand. Jinhua, how does it work? Can people speak directly, or they have to put it in the Q&A box?
They have the right to speak, and
okay.
Yeah.
Hello.
Yeah.
Yep.
Yeah. I'm Ranjan Dungel from Nepal. So thank you for very nice presentation. And my questions is the last presenter that he talked about the flood resilience things using that particular framework. So will it be applicable to the in the Himalayan region? That means the where it is sometimes it is very hard to determine whether it is flood or debris flow or flood is loaded with sediments. So how to deal in such a scenario with that particular framework? Thank you.
Yeah, I can go first. Maybe Huili, if you have any further comments, you can follow this up. So I think, thank you, Wenjin, for your good question. So I think yes, I think one of the probably biggest challenge of applying this kind of modeling, to Nepal, and actually, I think a wider low and middle income countries across the world, is the data. So because high performance or high resolution modeling, that means that we really need lots of data, to set up and validate the model, which is sometimes not available, in the data scarce context. So so for that reason, I think we like showing Huili's case study, we integrate this kind of modeling approach with open data from different sources. And because of time, we didn't mention, we also developed AI-driven, basically deep learning-driven approach to integrate and improve the quality of data from different sources, so that we can produce the high-quality data, to support this kind of I think simulation activities. And then talking about the sediment, so sediment transport, and also debris flow, and then landslide and things like that. First of all, as you can see from the growth modeling, framework we developed, at this moment we didn't consider, that function, in Nepal. And then the model itself, have a capability to simulate the detailed sediment transport, geomorphological changes, and the landslide and debris flow. And then potential there, but however, the data is even more difficult to get, for this kind of issue, different scenario. So yeah, I think we haven't really found out a way, how we can really model the detail sediment dynamic in the data scarce in a region like this. But I believe it's, with a more and more kind of, I think more rapid development in data, technology, like, for example, collecting data from different sources. Hopefully, in the near future, we can address this kind of challenge. I hope I answered your question.
Yeah, thank you. Yes, yeah, we have chat during your IRL presentation as well. So it's continue on that. So I also listened to your presentation in China, Chengdu, in last October. Uh, so and yes, it is definitely beneficial, but it's still I think there should be certain things where the data is very low and where the absence of data is very high. Even though we don't have the 100 years rainfall intensity data, and we have the high risk zone, and even sometimes it is very hard to distinguish whether it is flood or whether it is just flood or whether it is or the landslide even in the river channel. So that's why the challenges exist in the Himalayan belts. So that I'm very curious on this and I'm interested. Thank you, sir. Yes.
Yeah,
But
thank you.
you addressed my questions. Thank you.
Yeah, thank you. Yeah, I mean that's exactly the aim of the chair. So I think again we are facing lots of challenge in here, but I think the technology is evolving, and then hopefully through this kind of international and also multidisciplinary or even transdisciplinary collaboration, we can really arm ourselves with the best technology and to really address this kind of great challenge, grand challenge across the world. So basically, a simple word. I think simple word, we need to work together. Yeah, I think not only, and then we is a kind of broadly. I think similar people working in relevant fields to work together to address this grand challenge. Thank you. Looking at the chat, I think we got another question. Yeah, I think there's one question on the checkbox said, I would like to know what is the rate of accuracy of this simulation model. Are there any specific cases, region where models are applied, results be observed? Yes, indeed. So the model we using or developing, it's a entirely physically based model, hydrodynamic model, simulating detailed, flood dynamics. So in terms of accuracy, I think obviously that would rely on the data. For example, the DM, the digital elevation model, and things like that. That would really have a critical impact, on the modeling result. So the accuracy, more or less, related to the data availability. So I think, for example, the model now have been applied across more than 40 countries across the world for different type of flood modeling, and then forecasting, risk assessment, and things like that. So specifically in the UK, because where data it's more available, I think in high quality. So for example, in our paper in the application of high PIMS, like the result I show to the Eden catchment in the UK, we have a very good data set, for the from observation, like the detailed change of flow levels or water level, in 18 gauges. And also the flood extent, I think in a city area. So and then we carried out, a series of comparison, and also I think a sensitivity analysis, to this kind of, I think comparison. And then so basically, what I'm trying to say is the accuracy is depend. But I think if data, I think in good quality, and then the accuracy, can be achieved in better shape. Yeah. So another benefit of the model, I think, it's the I think another benefit of the model is because a physically based model, so the parameter is very limited. So I think we only really have the -n, the roughness coefficient, and also if we consider the infiltration and also soil data needed. So I think that's I think good for the model to apply, I think, in different area where the data, is scarce or engaged catchment, in other words. Yeah. Sorry, I think interrupt. Yeah. Can you? Yeah. I'm happy to take your question. Okay.
Yeah. Hello.
Yeah, I can hear you.
Yeah. There's a nice presentation. Sorry, I could not talk much, but I wanted to actually, is it applied? This model is applied anywhere? That's what I wanted to know. Because in our region we have a flood occurrence every year. So if I can adopt this model, means like in our region where data availability is very low, as well we don't have a set standard of data uh, due to many various factors and parameters. So I wanted to know, means if anywhere other applicable and what are the data sets that are required, so that we as a small state in India, we can try to make a standard set of data for this model to work out. That's your question.
Yeah, yes, simple word. I think the model can, it's a generic and then transferable. Again, if data available. So I think that can be adopted and applied in your region. So the data side. So obviously, we mentioned before the data is always challenging, but with the developing of the data analytics tools, now we have a lot of of way, and then including deep learning, to improve data quality by integrating data from different sources. So for example, DEM, and then we do have a lot of open source DEM. So I think, for example, I think one paper we published, I think probably 5 years ago now, I think is to how to create, the kind of high resolution, high quality DM from the open source coarse resolution DM. So the way we did it, it's we use London as a case study, and then using Zoom, and then now it's not difficult to have using LiDAR to kind of I think to collect high resolution data for kind of limited area, and then we use that to train machine learning, and then so that we build a kind relationship between the coarse and the fine data, and then we use that to generate high resolution data. So again, I can't say we have the final solution for that, but I think the model is applicable to anywhere, and then obviously the accuracy would be or reliability would be related to the data, but we are I think including ourselves and also lots of teams across the world, I think we're developing approach to address this. I believe that the situation will become better and better.
Okay, thank you, sir.
Thank you
so much.
Can I have one follow-up questions over here? I raised a hand, so sorry for me.
No problem. Yeah, okay. I just saw that. Yes, please, Ranjan. Yeah. Mm-hmm.
So I'm also from Nepal, and I want to do the follow-up questions on earlier two questions. So yes, have you yes, it depends on data, but whether this model is I graduated from Durham University, so I know the river monitoring system over there and the data that they reach in data sets. I do have we have the joint project. I did work with the Durham team in Nepal as well for generating data, and while doing so, they have developed their own database by we didn't have the rain gauge station, and so my questions is my queries I want to know is that how you models how this change in river bed or the river morphological physical parameters, how you have incorporated, because even in the catchment level you have explained in the catchment level, in our context even in the catchment level there is the use changes in the river gradient, bed slopes, and those type of river morphologies. And if you talk about the South Asia region, so Nepal, India, the river system is like the very connected, and it has long stretches, and even in the short width or even in the short river profile, we have the multiple type of the changes in different geomorphological parameters. How this model address those sorts of things, whether it is applicable in that context or not. So sorry for long questions, but yeah.
No problem. It's a really great question, actually. So I think a really great question. So that's the reason when I introduced HiPIMS, and then my colleagues, following my colleagues' instruction as well. So how HiPIMS, was initially developed, for flood modeling, but later on we extended, to expand it to a multi-hazard. For example, landslide, I think sediment transport, pollutant transport, and a range of things, floating debris, and also carbon human nature system, things like that. Because one of the great limitation of today's modeling tool for the disaster risk reductions, apart from kind of, I think a silo way of, coupling with human system is also to simulate this kind of multi-hazard, process. Like you mentioned, flooding can really lead to, a bed change and then geomorphological change or something like that. This doesn't happen in the real world. So, however, when we do, flood risk measurements, for example, we don't really consider them. We consider the environment is static. So I think when we start a simulation, the DM's fixed, and that there's no human activity, that's obviously would not, really like reflect the real world. But nowadays, when we do the risk assessment and risk management, because the budget, from government always limited. So how we can really like consider these kind of multiple processes, and then so that we reflect better in the real world, and then to develop, more optimized, approach, to support, I think disaster relief is important. So simply, I think, to your question, now coming back to your question, yeah, the model have the capability to simulate this kind of multiple processes, like even including like how flood, wave drive, sediment transport, and then bed change, and then erosion, and then even dam break and things, dam breaching process, and also, floating debris, I think how they interact with, for example, bridges, and also the affecting the scour and things like that. That's all in there. However, again, the challenge is coming from a data side. So I think especially for the sediment transport, anything related to sediment transport, we know that it's one of the most difficult thing to predict, is sediment transport, because I think it's so much diverse. I think the real world situation can affect the modeling results. So what I'm trying to say is that the model capability is there, but we still need to really test the model, and also collect data, how we can really better apply in the real world to reflect better the real world situation. So now the model can be used to, for example, produce a scenario, basically to test a what if scenario. So what if, for example, considering a bridge in the width of the river, and then how that I think affect the sediment, and then river geomorphology changing, something like that. And then we can only do that, but we cannot really use the model for some forecasting, predict what's going to happen, because the prediction may not be reliable, again, because sediment transport is so much complex to simulate. But I believe with the model capability here, and then the that would drive I think development from other fields as well. So I think more or less in research always you go first and then catch up, and I go you go for and then catch up. And I think hopefully I think that the capability overall would be rapid development, I think in the future years.
Thank you very much. It's very nice and good explanation. Thank you, sir.
Yeah, thank you. So considering the timing, we already 8 minutes past. Peter, I don't know, how the time, but I'm happy to stay for 5 more minutes if needed. But I think I'm also happy to close it. I think it's your call really.
I know Professor Grimas wants to give a final greeting.
Thank you, Petra. Thank you, Professor Quialang, and also to your colleagues for a very, very great presentation.
Thank you very much for your invitation. Yeah, thank you very much.
I have only one curiosity about your presentation. If you use usually your models also for preparedness purposes, with for instance for planning, emergency planning, something like that, because I think it's not only for disaster risk reduction for the intervention, but could be very, very useful also for the preparedness phase. I have this curiosity if you can answer very, very fastly.
Yeah, definitely. So I think, Stefano, that's a great question as well. The purpose of how Young's work is how we can really prepare to improve our preparedness, test different kind of scenarios again, because we all know that disaster cannot always be avoided. So no matter whether what kind of engineering intervention and nature-based put in place, we still have the residual risk. That means the case can still happen. If that's the case, and then emergency management and then preparedness, that would come into place. So and then with for example how Young's model in place, and then we can test different scenarios, and then so that we can really using AI with reinforcement learning, and then to produce some optimized decision. so that, we can really mitigate the risk, because real world is so complicated. Human brain, I'm afraid, may not be, I think, able to analyze all different scenarios and put all the data together at a short time to come up with a kind of informed decision. But AI have a potential to do it. So I think that's the reason I think that would be really, important, for short term and long term, basically answer what if, and then, also give data. And then can you give me, for example, the best, I think, response, for example, in emergency response, scenario, and then they can, give this kind of answer, and then for us to make the final decision. Yes, great question. Yeah, I think the answer, we are on the way, to do this kind of thing, basically firm the final digital twins, a kind of sexy word, sexy word we're talking about all the time. Yeah.
Thank you so much. I think that your models and also simulation is a good tool for and also artificial intelligence, of course, for exploring possible futures, and this permit to prepare in advance is another word that in the future, but also now we have to use is the anticipation. This means we can see in advance what can happen, and so we can start to prepare ourselves for. I think it's very important. Your work is very important. Also, if we remain in touch, the UNESCO chairs that are working in this topic, because the intersectoral and interdisciplinary approach, I think, make the difference if we are able to work together. So thank you so much, and we stay in touch also for the future talks in this channel of the initiative. Thank you so much.
Yes, thank you very much.
Thank you. Thanks a lot.
Thank you.
Yeah, thank you for inviting.
Thank you.
Yeah, thank you. Stay in touch. Bye.
Thank you.
Bye.
Bye-bye. Take care.